Hi, everyone. Thanks for joining in. Today, we'll be talking about how prime numbers keep the internet secure. And I'm super excited to talk about it today because it's a cool subject. But before we begin, I do want to preface this talk that there will be some math involved. It's not very difficult math. If you've taken algebra classes in high school or college, you should definitely have no trouble following along. But I do want to preface it because I know math isn't everyone's favorite subject. But like I said, I'm very excited to give this talk because I think this subject is very interesting, and it's a subject that's very close to me. It's actually very close to you as well. In fact, it's close to anyone who uses the internet, because whether you know it or not, if you're using the internet, you're using prime numbers. And you might be wondering, why are prime numbers so special? What do they allow us to do? So the answer to that is encryption. So if you're not familiar with encryption, encryption is a process of turning information into a cipher. And so a cipher is a secret code that no one can understand except for those that have the private key that can decrypt the cipher. And so encryption is very important to today's internet. It's basically the reason why our data is able to be transmitted securely across the internet. And it allows us to do simple things like registering username and passwords into websites like Facebook or Google, but also allows us to do complicated things like online banking. So without encryption, our modern day internet would essentially collapse. So encryption is the main focus of today's talk. So to kind of give some objectives of what I'll be covering today, I'll be covering encryption, like I mentioned. We'll be going over symmetric versus asymmetric encryption. I'll also be talking about public and private keys and how those work in encryption. And finally, I'll be talking about how prime numbers factor into all of this. The title of the talk is how prime numbers keep the internet secure. So we got to talk about prime numbers. So by the end of this, you actually know how to implement encryption yourself using some basic Ruby and some basic math. And so you'll be able to actually encrypt your own messages, which I think is pretty cool. So let's dive into it. So the first topic will be symmetric versus asymmetric encryption. So to give a little history lesson, up until 1970, the only form of encryption that we had was symmetric encryption. So symmetric encryption gets its name because it uses the same key to both encrypt and decrypt information. So to give an example of how symmetric encryption works, let's say that we had two users. One user is named Bob, one user is named Alice, and they've both agreed on a secret key ahead of time, which is the color yellow. So as a side note, these initial examples, I'll be using colors to denote different things like keys, messages, and ciphers. I think colors are a useful metaphor for encryption. We'll be getting to numbers later, but we'll be using colors first. And for anyone who has trouble seeing colors, like anyone who's colorblind, I've included the first letter of the color. So in this case, yellow, I have Y. And any colors I use, I'll be including the letter as well. Just want to make that side note. So yes, let's say we have two users, Bob and Alice. They both have a key, color yellow, and they both want to communicate via symmetric encryption. However, we have a third user, a third malicious user named Eve. And so Eve will be listening in on the conversation between Bob and Alice, and she'll be intercepting any messages that come between them. And so let's say that Bob has a secret message, the color red, that he wants to send to Alice. And even though he doesn't know that Eve is listening in, he knows that someone could be listening in. So what he's going to do is going to encrypt his message using his key to get the cipher orange. So he's going to send his cipher across the wire to Alice. Eve, listening in, will be able to intercept that message, and so both Eve and Alice will get the cipher. However, only Alice has the key, therefore only Alice is able to decrypt the cipher back into the original message red. Eve, however, does not have the key, and so she is stuck with the cipher orange. So symmetric encryption, in this case, symmetric encryption has worked. And so symmetric encryption does work overall. However, there's a problem. The problem is, how do we agree on a key ahead of time? Because in symmetric encryption, we use the same key for both encrypting and decrypting. So we need to have both parties who want to communicate need to have a copy of that same key. And the only way to securely get a copy of that key is to actually meet in person. Because we can't communicate with each other without having met in person. Because to give an example, let's say that only Bob in this case has the key. Alice does not have the key, so Alice is not able to encrypt messages to send to Bob. Well, Bob's thinking, okay, I'll send Alice the key, and when she has the key, then we can both communicate. But unbeknownst to Bob, Eve is sitting in. So if he sends the key over to Alice, Eve will then get the key as well. So in this case, Eve will be able to read all the messages between Bob and Alice. And not only that, she'll be able to go into the history and read all the previous messages that have been sent using the same key. So in this case, symmetric encryption is broken down, which is not what we want at all. We want to be able to send secure messages. So the question comes, how can we safely and anonymously pass messages to one another without having to actually meet in person to agree on a key? So the answer to that is asymmetric encryption. So asymmetric encryption gets its name because it uses two different keys for each process. There's a public key for encrypting the message, and there's a secret key for decrypting it. So the public key is called public because that is the key you share with everybody. It is totally safe to share your public key with the entire world, even with hackers. The secret key, on the other hand, is what you want to keep safe. If you have a public and private key, you're safe to share the public key, but you want to keep the secret key secret so only you know it. And so the way that public and private keys work in this case is that they're actually the inverse of one another. So if you use them both together, they essentially cancel each other, they cancel one another out. So let's say we had a private key that's color red. We would need a public key that was essentially the inverse or the complement of our private key. So in this case, if I had a private key that was red, my public key would be blue. And if we use them together, we actually cancel each other out into the color white. And so since we cancel each other out, that's how we're able to get back to the original message. So kind of give an example of how asymmetric encryption works. Let's go back to our Bob and Alice example. So in this case, let's say that Bob has a public and private key. And let's say that Alice has a message that she wants to send to Bob. What Bob can do is Bob can actually send his public key to Alice. So since Eve is listening in, she'll also get that. But that's totally okay. As I mentioned before, public keys can be shared with the entire world. Now, since Alice has a message she wants to send to Bob, she's able to encrypt the message using Bob's key to get to a cipher green. And so she will send the cipher back across the wire. And so Eve will also intercept the cipher. However, only Bob has a private key. So only Bob will be able to decrypt the cipher. And the way he does this is basically by combining his private key with the cipher. And since Alice used the public key, which is the kind of the first half, since now Bob is combining it with the private key, the public and private key cancel each other out. And so they're able to get back to the original message, which is yellow. So in this case, Bob was able to decrypt the cipher back into the color yellow, while Eve is stuck with just the public key and the cipher. And so Eve cannot use the public key to decrypt the cipher, but the public key can only be used for encrypting. And so the reason that Eve cannot use the public key to decrypt the cipher is because encryption is known as a one-way function. Technically, it's a trapdoor function, but I'll give the distinction in 1 second. So encryption is a one-way function, meaning that it works very easily in one direction. So in this case, if you had a message and you had a public key, you can very easily encrypt that message into a cipher. However, if you only had a cipher, it is very, very, very hard to then decrypt that cipher back into the original message without anything else besides the cipher. So in this case, encryption is a one-way process where you encrypt it in one direction, but you can't easily decrypt it. Unless, however, you have the private key. So this is what makes encryption a trapdoor function as opposed to a true one-way function. So a trapdoor function is a one-way function that only operates in one direction unless you have a special piece of information. So in this case, the trapdoor or the special information is the private key. So since Bob has the private key, he's able to decrypt the cipher back into the message. And there's a known way of decrypting with the private key, so it's a very easy process. So this is how Bob is able to decrypt the cipher without Eve being able to. Okay, so up until this point, I've just been using numbers to kind of give a foundation, or I've been using colors to give a foundation of what encryption is. But it's not a perfect analogy because encryption doesn't actually work that way with colors. You can't actually use colors to encrypt or to implement encryption. So in order to actually show you how encryption works, we gotta get to the numbers. So enough of colors, let's get to the numbers. So the encryption algorithm I'll be covering today is the RSA encryption algorithm, which stands for the Rivest-Shamir-Edelman algorithm. And it stands for the last names of the 3 cryptologists who invented it. That's what RSA stands for. And it is the most commonly used asymmetric algorithm for encryption today. It's used for a lot of stuff. I mean, a lot of stuff. So it's used for HTTPS, TLS, it's used for SSH, it's used for GPG, If you aren't familiar with those acronyms, don't worry, it's not important. I just want to let you know that RSA is used for a lot of stuff. And so there's two main components of the RSA encryption algorithm. There's the public and private keys, which we've gone over a little bit. There's also the process of encryption and decryption. So we'll be covering both of these components of the RSA algorithm, but we'll be starting with public and private keys because we'll need to know how to create public and private keys in order to then encrypt and decrypt messages. So now it's time for key generation and learning about how to generate public and private keys. And so this is actually the first glimpse we're going to get of prime numbers. So in the color example earlier in this presentation, I showed you that in the color example, I had the private key and the public key as one singular color. So the private key was red, the public key was blue. But that's not actually how RSA works. In this case, our public key is actually gonna be two things. Our public key is gonna be two different numbers, the number E and the number N. And our private key is gonna be a single number, the number D. So remember these letters right here, E, N, and D. I'll be using these a lot because this is the notation, this is the vocabulary of the RSA protocol. They use these single letter variables a lot. So I know it's not the best thing, but just what they use a lot. So I'll be using E, N, and D a lot. So just keep those in mind. So how do we actually create this public and private key? So there's 5 steps we're gonna need to do in order to create these numbers. And the 5 steps are right here. So you can notice, this is where the math comes in. So it's a little intimidating, but don't worry, we'll be going over it step by step. But the most important part of this entire process, you can see the output. The output is going to be a public key and an E, which I mentioned before, or E and N. Kind of, I mix them up, but it's the same thing. And the private key, D. So we're going to be going over these 5 steps to create our public and private keys. So you can see the first step is going to be choosing 2 large prime numbers, P and Q. Well, for our examples, we'll be using smaller numbers, so just kind of keep it easy. So for our case, and this for step 1, you can pick literally any 2 prime numbers as long as they're different. So I want to keep it simple. So I put P as 13 and Q as 17. So in order to keep track of these numbers and so don't forget, I'll be writing them down in a little Ruby doc I have open. So this, you can actually follow along with me right now because we're actually going to be encrypting, or we'll be actually implementing RSA right now. So let me just write down P equals 13. Q equals 17. So yeah, feel free to follow along with me. Tab back. Okay, second step is computing N. So N, as I mentioned, is the first half of our private key. So N is defined as P times Q. So in this case, our N is going to equal 221. So I'm going to write that down. So N equals P times Q. All right. All right, third step is calculating the totient of N. So the totient has a significant meaning in mathematics, but we're not going to be covering that right now because the meaning of totient is kind of outside the scope of this presentation. The most important thing for us is knowing that totient of N is defined as P minus 1 times Q minus 1. So I'm going to write that down. So I'm just going to write, so if you want to learn how totient is spelled, it's spelled like this. So it's P minus 1 times Q minus 1. Okay. If you want to learn more about how the math of RSA works and like things like totient and all that stuff, I will have some references at the end of this presentation that you can definitely use to dive more into like the mathematics if that's your thing. But for the purposes of this presentation, I'll be skipping over a lot of that stuff. But so in our case, the totient of N is going to equal 12 times 16. So it's 13 minus 1, 17 minus 1. So 12 times 16, and it's going to be 192. So that's a totient of N. So fourth step is selecting the value E. So E, remember, is the second half of our public key. So we can't just select any random number to be E. There is some criteria. The criteria for E is that it has to be between 1 and the totient of N. So we just calculate the totient of N. So it has to be between 1 and 192. And E must also be relatively prime to the value N that we calculated earlier. So as I mentioned, in order for 2 values to be relatively prime to one another, there has to be no other integer greater than 1 that divides them both. So for example, 12 and 13 are relatively prime to one another because no other value except for 1 divides into 12 and 13. However, 12 and 14 are not relatively prime because the value 2 divides into both 12 and 13, or 12 and 14. So that's kind of the definition of relatively prime. So we can pick any number that satisfies this criteria. So between 192 and also relatively prime to 221. So for the purposes of this presentation, I picked a nice small prime number. So I picked the value 7 because it's small and prime and also fulfills our criteria. Okay, so we have the value of E in this case. So E is going to be 7. Perfect. So up until this point, we've now calculated our public key. So it's 7 and 221. So that leaves us with our private key. So how do we get the private key? That's the last step of this process. So you mentioned, if you remember back in the color example, I mentioned the private key and the public key are the inverse of one another. So if you use them together, they cancel out. They essentially cancel each other out. So we know what the public key is. It's 221 and 7. So that leaves us with trying to figure out what private key is. And so we know that has to be the inverse of these numbers. But what number is actually inverse? We need to have some sort of formula that gives us the inverse of these two numbers. So the RSA protocol does give us this formula. So the formula for finding the private key is D times E mod the totient of n equals 1. So the first half of this is easy, D times E, simple multiplication. But we have this mod totient n. So what the heck is mod? So if you're not familiar with what the mod stands for, it stands for the modulus or the modular operator. And so if you're familiar with Ruby or JavaScript, it's the same thing as a remainder operator. So we can actually rewrite this algorithm right here to be D times E remainder totient n. So I'm going to rewrite it so that it's a little more familiar to us. So this equation right here is how we're going to find D. So we already know what E and the totient of n are. So we can plug those numbers in. So we got 7 and 192. But now we just got to basically solve for x. If you remember back to your high school or whatever the days where you did some algebra solving for x, that's what we got to do here. We got to solve for D. The problem is, I don't know about you, but I never learned how to solve an equation that used the remainder operator. And I'm guessing there's a high chance that you didn't either. So there is a way of doing this with an actual algorithm, and the algorithm is called the extended Euclidean algorithm. We're just going to call it EEA because it's a tongue twister. So we could use the EEA to find D, but the EEA is outside the scope of this presentation. And it's not super difficult, but it would take me a while to explain it. So we're actually going to cheat a little bit. So what we're going to do is, since we're using small numbers, we can just actually loop through values of D until we basically fulfill this equation. So what I'm going to do, as I mentioned before, I'm going to cheat a little bit. So I'm going to start with the value of 1. I'm just going to do a while loop, and then we'll break out of this loop if essentially this equation is true. So we got D times E remainder the totient. And if that equals 1, we'll break out. If that doesn't work, then we're just going to increase the value of D. And we'll end our loop. And so at the end, I'm just going to output what D is. Okay, so let's run this and see what our private key is. So 55. So 55 is the value of a private key. And so that's exactly what you'll get also if you use this actual EEA algorithm. So D equals 55. So awesome. So now we have both our public and our private key. 221 is our public key, and our private key is 55. So remember those numbers. Okay, so we finished the public and private key generation. Now we're on to encryption and decryption. So that's the last step of our RSA algorithm. But before I actually show you what the actual algorithms are for encryption and decryption, I want kind of a little brainstorming session. So how do you think encryption might actually work? So we do know based on what I've said earlier in this talk, there is some criteria for encryption. So since we're dealing with numbers, we know that encryption has to be some sort of math equation. We also know that encryption has to use our public key. We have 7, 221. So it has to use a number in some way. But the most important thing that I mentioned earlier is that encryption is a one-way process. It's a one-way function. So it can't be reversible, meaning we can't use math operations that are reversible. So we can't use addition, we can't use multiplication, because, for example, if I had a message and I just added my public key to it, a hacker could easily just subtract the public key and then get back the message. So that wouldn't be very secure. So the question is now, what math operation can't be reversed? And the answer to that is something we've actually seen earlier in this presentation. The answer to this is the modular operator, or also known as the remainder operator. Because if you think about it, if I gave you this equation of x remainder 10 equals 5, and I asked you, what is x? There wouldn't be a singular number. It could be a multitude of things. It'd be 5, 15, 25. It could be any number that when you divide by 10 has a remainder of 5. So there's not any singular number or singular answer to this equation. So basically the point of this is that encryption and decryption depend a lot on modular arithmetic or math involving the remainder operator. So with that said, here is the actual algorithm for encryption. So encryption is m to the power of e, remainder n equals c. So let's break that down a little bit. So m is our actual message. So if we have a message that we want to encrypt, we're going to raise our message to the power of e, take the remainder of n, and we'll get our cipher. So in this case, m has to be a number. So if you're dealing with string data, like if you want to encrypt a string, there are ways to turn strings into numbers, but I'm not going to cover that right now. I'm just going to assume that our message is going to be a number. So and you can see e and n. So we're using our public key right here. So it's our message to raise to the power of e, take the remainder of n, and we get our cipher. So the decryption is actually very similar. So decryption, you take your cipher, you raise it to the power of d, which is our private key, and you take the remainder of n, and you come back to your message. So it's actually not too difficult. And I can prove to you, so let's prove it right now that this actually works. So let's get out of here. So I have a server running right now on my computer, and the server will accept a public key. It will then encrypt a message with that public key I give it, and give me back a cipher. And it'll be on me to try and decrypt that cipher using my private key. So it's very similar to the Bob and Alice example. So imagine I'm Bob, I'm sending Alice, the server, my public key. Alice is then going to send me back a cipher using that was encrypted with the public key, and I'll be able to decrypt it with my public key. So let's send a curl request to my my server. So you can see my server running right now is at localhost port 4567. I'm passing a key, and so you can see E right now is 7. So I'm attaching it with a plus sign just so I can denote it. I can separate both the E and the N. So my server is going to take this, and it's going to return to me a cipher. So the cipher returns to me is 185. So if I was a hacker right now, all I would see is 185. But since I have the private key, let's see if we can try and encrypt this or decrypt this message. So we know the cipher, so we can do cipher. I'm going to raise it to the power of our private key, so 55 right here. And we're going to take the remainder of 221, which is n. We should arrive back at our original message, so 42. So let's see if that was actually the number that the server sent me. So I have my server running right here. So you see, got the public key from my client and a message for the client. So it sent me message 42. So we were able to decrypt it, 42 being the answer to the universe, for those who don't know. And I can actually show you the server code right here. It's a very small server. It's a server running in Sinatra. So this is a server code. So you can see I got the key from the client, so the client being me, split it out based on the plus sign. I have a hard-coded message, so it always returns 42. And so you see the encryption right here, it's the same exact formula as we have here. M to the E, M raised to the E, power E, remainder N equals C. So message raised to the power of E, and then take the remainder of N. So you can see right here that we were able to both encrypt and decrypt the message. So we were able to encrypt our messages right now with using some pretty simple math, to be honest. Like it's just using some exponents and using the power of the remainder operator. So it's a pretty simple formula if you kind of break it down a little bit. So now the question is, if it's so simple, why is this so secure? You know, why do we use RSA encryption for literally almost everything? Why does it kind of has its hand in kind of everything? So to kind of see why this is so secure, let's step into the shoes of a hacker. And let's pretend that we're a hacker. Let's say we're Eve. We've been able to intercept both a cipher and a public key. So we have a cipher and we have a public key. So now let's try and decrypt that cipher. So let's go step by step. So if we have a cipher, in order to decrypt the cipher, you need the private key, as denoted by this function right here. Well, in order to generate a private key, we need to know the token of n, as denoted by this function right here. This is where we solve for d. Well, in order to know what the token of n is, we need to know what p and q are. So as I said before, token of n is defined as p minus 1 times q minus 1. Okay, well, all we need to do now is just solve for P and Q. And so in order to get that, we just need to factor n, because n is defined as n equals P times Q. So we can just break down n into its prime components. P and Q will be in the clear, and we'll be able to get the private key. The problem, so this is known as prime factorization, where you take a number and you factor it down to its prime components. The problem is prime factorization is really, really hard. Prime numbers in general, determining what a prime number is, or determining if a number is prime, is very difficult. To kind of give a sense of how difficult this is, say we had, P and Q. Say we knew the values of P and Q. In order to multiply them together to get the value of n, it's a very easy process, multiplying P and Q together. However, given a value of n and being asked to then factor that into the two numbers that made it up is very hard. Because in the first case, we just need to multiply two numbers together. In the second case, we need to literally loop through all the combinations of P and Q to find the correct combination of P and Q. And so to give a sense of how long this takes, if we had two numbers of P and Q that were on the order of 1,000 bits long, so we had a number that was about 1,000 bits, it would take us about 12 seconds to multiply both those numbers. To factor n, if it's around 1,000 bits long, would take 3 billion years. Now think about that. We have a computer, and all it's tasked with doing is breaking up one number of n into its two prime components, P and Q. If that n is 1,000 bits long, like a very, very large number, it would take 3 billion years to do that. So that is why the RSA encryption algorithm is so secure. It's not that it can't get cracked. It would just take multiple lifetimes in order to get cracked for a single value of n. So that right there is why prime numbers keep the internet so secure, because it's very difficult to determine if a number is prime. You have to basically essentially brute force through it. So we'd have to brute force through all the possible combinations of P and Q in order to find out what n is, to then reverse engineer our private key. So that right there is why prime numbers keep the internet secure. So before I end this talk, I made one claim at the beginning of this talk where I said that if you use the internet today, you're using prime numbers. So I just want to give some proof to that statement. So I've been explaining RSA encryption in a vacuum. So I'm telling you this is how it works, but I want to actually show you that this is how it is, so you actually believe me. So what we're going to do, so for those of you who've taken 170, you've probably learned about TLS a little bit and HTTPS and the protocol for that. So what I'm going to do is I'm going to send a curl request. I'm going to send a curl request to Launch School. And I'm going to see, since Launch School uses HTTPS protocol, we'll see that there's a TLS handshake occurring. So in the TLS handshake, what happens is, since Launch School uses the HTTPS protocol, it is trying to tell us that we can establish a secure connection. So the TLS is a secure connection. And in order for my client, so in order for my computer to trust the Launch School server, it has to prove that it is who it says it is. And it does this through something called the certificate of authentication. So the certificate is going to prove to me that the server I hit here at launchschool.com is the actual Launch School server and not some hacker posing as the Launch School server. And so you can see in this TLS connection that we're using, there's the RSA right here. So it's using RSA algorithm for authentication. It's using it in this certificate of authentication. But let's prove it a little more. Let's actually go into that certificate and find Launch School's certificate of authentication and find its actual RSA data. So what I'm going to do for that is I'm going to use something called Wireshark. So Wireshark is a program that allows me to see all the different requests that are coming into my Wi-Fi. So I'm going to click here. So what I'm going to do is I'm going to take the IP address of Launch School. I'm going to filter all requests by that IP address. So I'm going to do that. I'm going to reinitiate the message. So I'm going to send it again. So you can see here, here's all the requests we've sent. So this is very similar to what we saw before. So you can see client hello, server hello, certificate. That's very similar to what we saw here. Client hello, server hello, certificate. So let's actually dive into the certificate and let's see Launch School's actual RSA information. So we can do that. We're going to click on the TLS layer, and we're actually going to the handshake protocol. We're going to go to the certificate right here. So we're going to certificates. Okay, so you can see, let's go into the actual certificate for gotealeaf.com. So for those of you who don't know, gotealeaf is actually the old domain name for launchschool.com. So let's go into gotealeaf.com. As you can see, identifier, algorithm identifier is SHA-256 with RSA encryption. So it's using RSA encryption for this signed certificate. So if it's using RSA encryption for the signed certificate, we should actually be able to see the public key. So let's go into the signed certificate. As you can see right here, subject public key info. So let's click that. And so the algorithm for this public key is the RSA encryption. So that's something we know. We covered this in the presentation. So the subject public key, well, this is actually very familiar to us. We have a modulus right here. We have a public exponent. This is N, the modulus is N. The public exponent is E. So if we wanted to, we can actually send encrypted messages using Launch School's public key info right here. So that's proof to you right there that if you're using the internet and you're using the HTTPS protocol, you're using prime numbers, because these numbers right here are made up of prime numbers. So yeah, that is the presentation for today. So thank you for all for coming out. I hope you learned a lot of stuff. Here's the references I mentioned before. So if you want to dive more into the RSA protocol, like if you want to learn the actual mathematics behind it, here's some good good references. So Khan Academy has some great videos. If you want to see RSA actually implemented totally in Ruby, like a very robust implementation, you can check out this GitHub repo right here. And if you want to learn more at the EEA, I kind of skipped that over, but if for some reason you're a math guru or a math whiz and you want to learn more about that algorithm, click that link right there. So thank you very much. And if you have any questions, please let me know. Q&A. So is any part of the prime factorization under threat by the rising AI and or massively parallel computation? That's a good question, actually. So I didn't put that in this presentation because it was getting a little long, so I wanted to add too many parts. But yes, not AI specifically, but quantum computing is the actual main threat for this, because quantum computing is essentially much faster than everyday computers. So it has been shown that large mainframe quantum computers that can execute calculations at massive speed, in those cases, yes, those computers can actually break down and do prime factorization pretty quickly. It's not necessarily a threat to us now because it still takes them a while and those computers aren't very accessible. But yes, to answer your question, quantum computing is the main threat to this prime factorization and to RSA encryption in general. Any other questions? Also, feel free to ping me in Slack too if you have any questions that you think about afterwards.
You have a question in the chat.
Oh, chat. Let me see. Can I see the chat? I'm not sure. Oh, more chat. Okay, here we go. Is it possible to save all possible key and Qs ahead of time, that when you're given N, it has to be one of the values you figured out ahead of time? Is there a library that people create over time to reverse N, or there are too many possible values? It's just too many possible values, because we're talking about values of N that are 1,000 to 2,000 bits long. It's hard to give an example of that, but for example, with Ruby, for example, let me give like a quick example. If I went to IRB, so there's a library that allows you to basically generate prime numbers really quickly. So it's called OpenSSL. So OpenSSL, I'll do big number. And I can generate, so this library allows me to generate primes. So I can generate values of P and Q. And so if I generated a value of generate prime that's 10 bits long. So this is just 10 bits long. I did 2 integer, 2 I. So that's not very big, but say I go to 1,000. I think it's gonna be actually too big for my computer to even handle. So that's 1,000 bits long right there. Let's see what 2,000 bits long is. I think it might be too big for my computer. Oh, it's working, it's chugging along. But you can see right here, in order to create just even one value of P that's 2,000 bits long, you see my computer actually have crawl into going to a crawl right now. It's gonna take a while to actually generate that number. So to do it ahead of time, you know, I'm not saying it's not impossible, but there's just so many there's so many values that could be that I think it's just not really feasible. And you know, if they did do that, then you could always just make the value bigger. And so instead of being 1,000, 2,000, you can make it 3,000 or 4,000. So I think it's just the sheer number of possibilities that could be makes it not very feasible to calculate all the possible values of P and Q. So I hope that answers your question. All right, so we got one question. So if every government is storing every other government's messages that have been sent, they may be able to fairly easily decrypt all this information later with more advanced quantum technology. Presumably, the value of the information will be decreased as it ages as well. Okay, so one thing actually I have to point out is, so HTTPS doesn't actually use RSA encryption for encrypting the actual messages. So I didn't mention this because I just wasn't too much information. But HTTPS protocol actually uses both asymmetric encryption and symmetric encryption, because asymmetric encryption is very, very slow. So what it actually does is it uses the RSA protocol to encrypt the symmetric key and then sends it over to the other user. So it will actually encrypt the symmetric key. So in that case, both users will have a symmetric key. So yeah, it's possible, you know, that with all this information storing, you know, they can decrypt these messages and then decrypt the symmetric messages as well. But you know, HTTPS protocol is a very robust protocol. I'm not saying it can't be, you know, cracked, but there's a lot of thought into kind of the TLS and HTTPS protocols. And I think, you know, I'm not sure actually how the government stores information and all this stuff. Like they could be able to store it in plain text. I'm not sure if they're actually just storing ciphers or anything like that. So I have no idea how the government does it, so I can't really speak to that. But I will say that, like, just being able to crack one RSA key does not necessarily entail you to being able to crack everything. But yeah, for that answer, I can't really know. I don't really know. So are other technologies still using synchronous encryption, not as secure, so they should be switched to asynchronous encryption? Is there anything currently still using synchronous encryption? So yeah, so I mentioned before, HTTPS for the actual messages. So when I send a message, or if I hit an endpoint at launchcode.com, it will actually encrypt using symmetric encryption. But the thing is, when I first established a connection with the LaunchCode server, we traded public RSA keys. So in that case, we were able to encrypt a symmetric key, and then once we get the symmetric key, then we're able to use symmetric encryption because it's much faster to do that. So HTTPS still uses symmetric key under the hood, but it first uses asymmetric encryption to then encrypt that symmetric key, if that makes sense. But in terms of like technologies that use asynchronous, I think the more worry, like, so if you're using the internet today, the bigger concern is going to websites that only use the HTTP protocol. So to give an example, so you can see here on this URL, Google is using HTTPS, so it's using, you know, an encrypted pathway. But if you ever go to a website that has just HTTP and not HTTPS, that is insecure. So it's sending all information in plain text. So typically, most websites that use HTTP are just kind of simple websites that I don't actually send crucial information. But for example, if you were going to a bank, and if a bank that you're using uses only the HTTP protocol, that's a big concern, because, you know, a hacker could then just kind of listen in on the communications and get all of your bank information in plain text. So that's a big concern. When it comes to technologies using synchronous encryption, that one I'm not so sure about, but I just wanted to say that if you're using a website that you're concerned about data security, make sure it's using HTTPS and not just HTTP. I'll give it a second in case anyone else has a follow-up. Yeah, these are all great questions, man. I wish I had more information about government cracking and quantum computing. I wish I'd said that more, but yeah, great questions. I hope you guys follow up and do your own research. You can tell me what the answers are to these questions. All right, so I think we'll end
one more
there.
question in chat.
Oh, I keep missing it. Okay, chat. Come on, oops, that's a chat. To clarify, it's a combination of prime factorization and the remainder that makes it irreversible, not just prime numbers. So yes. Well, prime factorization makes it so it's very difficult to get the values of P and Q. So the remainder operator makes it so it's hard to guess what the cipher is. So for example, the remainder operator makes it so you can't use the public key to decrypt the cipher. Because for example, if it was just M times E or like M times E and N, a hacker can then just do M divided by E and N. And they would be able to decrypt the cipher using the public key. So the remainder operator makes it so you can't use the public key to then decrypt the message, because you need to have that private key. You need to have the other half of that public key to decrypt the message. So I think the remainder operator is meant for just making sure encryption and decryption are secure. Prime factorization is making it so a hacker could not then generate the value of D, which would then be able to make them so they could decrypt your messages. I hope that makes sense. And I think I've got all the questions. So John, let me know if I missed any.
No, all good.
All right, cool. So like I said, if you're typing right now and I'm not able to see it, just ping me in Slack and I'll definitely answer them for you. But I think we're all good on questions, so we'll stop here. Thanks everyone. Thanks for coming out. I hope you learned some good information.